Hi everyone, and let's continue the lecture about introductory concepts in calculus. So let's discuss the fundamental theorem of calculus briefly. No? So suppose that you have a function f that is continuous on the interval a and b. Then we have two theorems of calculus. So the first one is we have g of x is equal to the definite integral from a to x of f of t dt, then g prime of x is equal to f of x. So what does this first fundamental theorem of calculus say? That if you have a given function, say f of t, then the area under the curve will be the integral g of x. And a corollary to this is that the derivative of this area, okay, the derivative of this area is your function. So there is some relationship between the area and the derivative, or the area and the slope. Okay? So the second fundamental theorem of calculus basically says that I'll just read this down first. So the definite integral from a to b of f x dx is equal to f of b minus of a, where f is any antiderivative of f. That is, f prime is equal to f. So what it basically means is if you want to evaluate an integral from the limit a to b, what you have to do is to evaluate the integral of the function f of x into a capital version. So if you say f, no, if it becomes capital, that basically means it becomes an integral or an integral of the function. So the integral of f of x with a small letter will be a larger letter or the capital letter f of x. Okay, again, f of x, if you integrate this will become a capital letter f of x, basically. So if you have here b, basically means you have to evaluate the given function, the given integral function at the value of b, or the upper limit. So the difference of this f of b and f of a is equal to the definite integral of f of x from a to b. That's it. That's what I'm going to discuss for now regarding the fundamental theorem of calculus. And knowing that, again, the area under the curve is just the definite integral. We call this the definite integral actually. More to that later. We could determine the area under the curve. So let's say we have a given graph of a linear piecewise function. Let's determine the definite integral, given here. So the first one here, we have the definite integral from 0 to 1 of f of t dt. Don't get too overwhelmed with the symbols. It is fairly simple. No? So what does this mean? So 0 means this is the 0 here, and this is the 1. Now when x is equal to 0, when x is equal to 1, basically, so this is x equal to 0, x equal to 1. So the area formed by this function will be this. So ito yung first problem natin. And for the second problem here, let's break it down first. No? So 5 to 7, and given function f. So we have 1, 2, 3, 4, 5. So this is your 5. So x equal to 5 is this. And another value of 7. So we have 6, 7. So this is another value. So this is your second problem. And then for the third problem, we have 2 to 5. So 2 to 5 here will be this 2. So x equal to 2, this portion, and then up to 5. So the total area will be this and this. So we have here this 3, including this positive and negative. So always remember, again, this is positive, this is negative. Over x-axis, positive, under x-axis, negative. Okay, so let's evaluate this definite integral from 0 to 1 of f of t dt. And basically, again, this is just the area of this rectangle. So the area of this is, so this width here is just 1, and this height here, so what is this height here? Graphically, we have 1, 2. So we have 2. So the area of this is just 2 times 1. Therefore, this is equal to 2. That's it. That's simple. And then another one, we have from 5 to 7 of f of t dt. We have here, so we have this number 2. So this is the area of the trapezoid. So we have this trapezoid. Or actually trapezium. To make this general. Okay, so we have here a length of 1 here, and then 1 here, another 1. And then the height here will be 2. So we have here a rectangle, no? And a triangle. So the area of the rectangle plus the area of the triangle. So we have 2 times 1 plus, so the area of a triangle is 1/2 BH. So 1/2 times base times height. So we have here 2 plus 1. So therefore the answer is 3. Very simple. So the integral from 2 to 5 of f of t dt. Okay, so again, the area we're trying to look for is this region. So we have a rectangle that is positive, a triangle that is positive, and another triangle that is negative. So this is positive, this is negative. Okay, so the base of this first triangle is 1. The height is, we have here 1, 2, 3, 4. So we have 4. And then the other triangle, the base is 2. And then the height is 2. Right? So we have here 1/2 base times height. So 4 times 1 plus another 1/2, 2 times 2. Okay, so this will become 2 plus 2. So therefore the answer is 4. Okay, so that's it. So that is the definite integral of a given function if we have a graphical representation of the function that is a linear function. Okay, so let's move on to the properties of definite and indefinite integrals. More on to the definite and indefinite integrals comparison. Let's focus first on the properties. So let's say we have here a given integral from a to b of c dx. If we visualize this using a graph, we will see this. No? So basically your a and b are the limits. Okay, so we have here a and b are the limits. And your function here is c, which is a constant. So be mindful, guys, c is a constant. So if the height is constant, then this will be just a straight line. So the total area of this rectangle will be the width or the base, and then the height. So sorry, the height pala ito. I got it flipped out. So the base here is the difference between a and b. And then the height will be this c. So that is why the integral of this function is c of b minus a. Okay, and then another one, if let's say we are adding or subtracting functions, but in general, I will just show you the adding. If we're adding two functions, basically we're adding these two heights. If we graph this visually, let's say this is your f function, and then this is your g function. If you add these two heights, guys, if you add these two now, so we have this first height and another height, here it will form this. So the addition of this height and then addition of this height, you will have this. So what happens here? If we add two functions, we are basically adding their height. So therefore, the integral of this function will be the total area added to. No? So the integral of this will be distributed to each of the functions. Alright? Okay, another property. So if we have a constant, we don't have a graphical representation now, but if we have a constant times a function, we could, what do you call this? We could factor out the c. And then another one, if we have a given function, it looks like this. And if we graph this function, for example, we have this from a to b, what we could do is we could break this into two or more integrals. Assuming that it is integrable from a to b, that is also a continuous function, we could separate the integral, no? So we could have this first integral, no? So the first integral, and then for the other one, another integral. We could add these two areas to find the total integral. So it could be represented as an integral from a to c and another integral from c to b. So this is the answer or the evaluation of this. Okay, so we could break this down into some value of c. Okay, all right. So that would be all. No, okay. We have another one. Okay, so if we swap the limits here, we can also negate, or the area becomes negative. So there is some sort of direction with regards to integrals or definite integrals. Let's say you have this again, this function. The computation of this integral will be, there will be some directionality. So from a to b, that is positive, but if from b to a, this will become negative, basically. Okay. And then if you have a same interval or the same lower and upper limits on your function, then therefore now if you can imagine, if you have this function, let's say you have a here, and since a, so from a to a, you have no area to form here, therefore this will be equal to 0. Okay, so that will be all for this video. I'll see you guys again.